So we are at a spot now where, yes, Marcus.
Do we have to take the final?
Yes, you do. AP test. The specific reason I'll tell you, I do that first semester. I do not do it second semester. The main reason why I do it first semester is because we are at a spot where you've got the three major types of describing motion. This actually perfectly fits in with what I was doing, so let's just go with it. What are the three types of describing motion? Kinematics. Energy. Forces, correct. So those are the three main ways of describing motion. Meaning if you look at a problem, you should really be starting with either kinematics or sum of forces or one of the two types of energy, which we'll address here in just a second. So basically the test is going to be, the final is going to be a problem or two that uses all of those things. And again, it's not trying to blow you out of the water. It's not trying to make them overly complicated. They are probably going to be problems that are comparatively to other problems in the chapter relatively simple, but it's going to be one connected into the next, connected into the next. Meaning like you might have a ball sliding down a hill. So you got to use sum of forces to figure out acceleration. And then it tells you it started from rest and the length of the hill. So you got to use kinematics to figure out how fast it hits the bottom of the hill. Okay, now the hill is sliding and there's friction. So you got to use forces to find out how much acceleration, blah, blah, blah. Maybe you find the speed that it leaves a ramp. And then you could either use 2D kinematics or energy in order to calculate how fast it hits the ground, blah, blah, blah. So that being said, energy is split into two camps. There are two big equations that you will start either of your problems with for the most part. What is one of them? What's that? No, I'm sorry, we're misunderstanding here each other. Okay, there are two major equations that are kind of involving all of these different things coming together. Okay, the first one that we discussed was, what's that?
Isn't it mechanical, isn't it, it's like a sum of forces type thing?
You're there-ish.
It's network. All initial plus.
I'll start with that one. Network is equal to change in kinetic energy. This is known as the work kinetic energy theorem. Okay, it's the first entire half of this chapter. We spent about 3-4 days on practicing this guy. What is work? How do you get all the sum of works? How do you change kinetic energy? Blah, blah, blah. We did the second one last Friday, and it is the conservation of mechanical energy. What are the three types of mechanical energy?
Kinetic, elastic, and gravitational.
Yep. I'm gonna do the thing so potential, elastic, potential, gravitational. Yep. So we'll go through more of this today. And as we discussed, do you always have to write all three? No, you don't always have to write all three. When do you not have to write them?
When they cancel out.
Nope. Just because they cancel out. If they cancel, I still want them up there. When do you not have to write them at all?
Definitely not.
No, that's not why. Because if they're zero, I want to see you canceling them out. I'll show you examples of it. The answer is when it's not changing at all in the situation. So, for example, the two examples that we did at the end of Friday, one of which was a roller coaster, right? So you look in a roller coaster and you go, all right, is gravitational energy changing?
Yeah.
Yep, absolutely. So we put it on both sides. Okay? Is kinetic energy changing?
Yeah.
Yes, we put it on both sides. Was elastic energy changing? There was no elastic force, so there was no elastic work, so there is no elastic energy. So we don't really need to write elastic in that particular case. Or the last problem we did, we had some kind of toy shooting horizontally, and we were looking at it right when it was right here, as well as right after it left. So in that example, is kinetic energy changing? Yes, absolutely. Is is the elastic energy changing? Yep. Is gravitational energy changing? No, because it stays at the exact same height, even though there arguably is gravitational energy and would be if it fell to the ground. Since it's not changing, we don't write it on either side. Now, that being said, if I do this toy thing and I shoot it at the ceiling, or actually I need to shoot it so that it doesn't hit. There we go. Well, I was trying not to hit the ceiling. Let's try it again.
Did a whole lot of
We did. Yeah, there you go. Well, it's shooting too hard. Okay, so it hits the wall over there. We're trying to figure out how fast it hits the wall. In that example, is elastic changing? Is gravitational changing? Yes. Is kinetic changing? Yes. So you would do all three of them in that particular case. How are we doing so far? Okay. Now let's talk about this real quick about when to use what. Okay. How do I know, Spainhour, whether or not to use the right one or whether or not to use the left one? Well, the left one, as we discussed, has based on work. And I can put any work of any possible force. But we said over here, mechanical energy, conservation of mechanical energy is actually not a legitimate law. What is the law? Well, it's a little bit broader than that. So for example, looking at the tree real quick, this is the conversation that Marcus was starting just a second ago. Energy splits off into two camps. What are they? Yeah, let's go pretty quick here. Mechanical, non-mechanical. Okay, I'm not going to do all of it, but mechanical splits into kinetic and potential splits into gravitation. Yeah, gravitational and elastic. And that's why these three, the sum of those is mechanical energy, right? So, is the conservation of mechanical energy actually a law that always happens? No. I've done this a few times, but here's a proof of it real quick. Does this have mechanical energy? Yes. Specifically what type? Gravitational. Wait, and does it have mechanical energy anymore? No. So, mechanical energy was not conserved. Okay, so when does this have to take place? Well, we said this. When does energy stay over here entirely in mechanical? Remember the right side of this after I drew this, blah, blah, blah. What forces are? Conservative. And what are the conservative forces?
Gravitational.
Gravity and elastic. Basically, these are the only things that can do work. If these are the only things that do work, congrats, you're golden, and you can do conservation of mechanical energy. Is that realistic? No, but it is an approximation that can work in certain cases, like, for example, roller coasters. Okay, force normal is in a roller coaster, but force normal is not doing work. Gravity's in a roller coaster, but gravity is conservative. What non-conservative force is regularly in a roller coaster? Friction. So, is mechanical energy actually conserved for roller coasters? No, it's not. As a matter of fact, in real life situations, it's almost never, but it's pretty close to, so it's a decent approximation. So for example, in conservation of mechanical energy, we would say, hey, you've got a roller coaster starting on top of this hill. Okay? To conserve mechanical energy, could the roller coaster ever go to a higher hill?
With a chain.
With added work, sure. But conservation of mechanical energy would mean work can't be done by non-conservative forces. That would be a non-conservative force. So, can it go to a higher hill? No, it couldn't go. But, according to conservation of mechanical energy, could it actually go to the same hill?
Yes.
In terms of conservation of mechanical energy, yes. In reality, why can it not? Because friction does work. Okay, so your biggest thing to let you know which one of these I'm going to use is there any work done by non-conservative forces? If the answer is no, right, there's no friction, normal's not doing anything, there's not any rockets, nobody's high-fiving, nobody's adding any extra forces in, then this over here is definitely going to be your easier bet, and you can do this relatively quickly and easily. On the other hand, if there is work done by non-conservative forces, then boom, you're over here. So I've done the roller coaster example twice, okay? As a matter of fact, I tried to set up the picture the exact same way both times. In the first instance, I was using this guy on the left, and the answer to why I was using that guy on the left was we had friction in the problem, right? On Friday, we basically did almost this exact same problem again, but we ignored friction, so arguably I would say it was vastly easier to use the one on the right. Everybody understand that? Okay, that's kind of one of the key things to get conceptually out of today. The rest of the day is going to be me practicing, especially for anybody that was not here Friday. Okay, Quick reminder, what are the individual equations? What's the equation for kinetic energy?
1/2 mass times velocity.
Very good. Technically speed, but I got you. Okay, what's potential of gravity?
In mass times gravity times height.
Yep. And what about elastic?
1/2 k times delta x squared.
Okay. So we're going to look at a situation here. And at the end, I also add that several times in this chapter, I've had this whole conversation about when you're using these versus forces in kinematics and when it actually becomes necessary to use energy. And the answer to when it's going to use energy is if you think about the force diagram in the situation, the force diagram is probably changing a ton, right? Like the roller coaster problem. The roller coaster is changing its force diagram a ton, so acceleration is changing a ton, so kind of acceleration and kinematics are entirely off the table, then we have to be using energy. So let's look here at a trampoline, okay? We have a person jumping on a trampoline. Because it matters, you can just make this up. What is the mass of a decent person? A decent sized person, not like decent morality wise. Not like that moral people have a different mass than non-moral. What's that? 70 kilograms is great. Roughly 150-pound person. Maybe a little less. All right, so here we go. This person is going to jump up and down on the trampoline. Okay, I'm going to kind of draw a little bit less of a 3D picture here because I think it's going to become a little bit more complicated if we do. So here it is where the trampoline is stretched. Okay, what is a normal distance? What would you say is a normal distance from the top of the trampoline to the ground? Meter? Yeah, I think that's reasonable. Meter, maybe a bit higher, but it's fine. Meter's fine. Okay, so I asked that to then say, what is a reasonable distance that the trampoline could be stretched? A third of a meter. Sure. Okay. So numbers aren't quite as complicated. We'll say it stretches about 40 centimeters or 0.4 meters. All right. If that's the case, give me what do you think would be a reasonable height for this person to go? 6. Don't say meters.
Don't say meters.
Don't say meters. 6 meters. Think about that in your head. This is 3 meters. I mean, to be fair, you could be a little bit ridiculous here and calculate these subsequent calculations, but
you said 2 meters.
I mean, that's still pretty springy, but I'm fine with it. Okay, let's say this is, I'll tell you, that seems a little bit, if I'm thinking this in my head, it does seem like those are particularly strong springs. But if you go to like the jump, Sky Zone or whatever, they do have those more springy ones that are, okay, so we're going to look at right now, just based on this information, what is the total K of this situation? Now I say total K because you guys have probably seen a trampoline. You know there's actually a crap ton of springs. There's a large amount of springs here. We're going to kind of treat this as though the trampoline is one big spring as opposed to a bunch of separate, make it more complicated. This is the question right here. So here's your circumstance. Now, the problem with students setting this up is simply that they go, well, Spainor, what's the initial and what's the final and how do I know? Okay, let's start with this. Which of these two methods, I mean, I know you probably know based on the fact that we're practicing this, but let's make sure we understand it based on this. Which of these two methods should I probably use and why?
Network.
Agree to disagree?
I'd say mechanical.
Conservation of mechanical energy. What about this situation? What about work non-conservative? Do you see here? Is the elastic a conservative force?
Yes.
Is gravity a conservative force?
Yes.
What are we probably doing with friction? So therefore, everything is conservative, and we can go right over here. Does that make sense?
Yeah.
Yes.
What is U?
U is potential energy.
Okay.
The potential energy of gravity, the potential energy of elastic.
Is the K kinetic energy or is it two
Now, that K in that particular setup is, remember, elastic is another name for spring, right? So that is the K from the spring force. As a matter of fact, the force that goes with each of these, if it helps, force of gravity is mg, which we see right there, right? Force of spring is, well, the absolute value is K delta x, which you see one of those right there. Yes?
So from coefficient, what is that called?
Spring constant?
Spring constant. So it's lowercase, and then for kinetic it's capital.
Now, I'll tell you in truth, if you continue forward in physics, not that any of you have to, if you continue forward in physics, we use the same letter so many times. Like, you guys have used the Greek letter mu for just coefficient of friction. It comes back in so many different capacities, as do all of the letters. We use M in like 9 different ways, and yeah, it's V is used for voltage and velocity, and it's all about context and just understanding. But let's go from here. All right. So here's our question: what is K? Well, first thing we kind of figured out is that I should probably be using this, and we figured that out because the only forces doing work are gravity and elastic, and those are conservative. So when you start here, there's 2 things you need to do to start off with, because I've given you a very generic situation. I haven't told you specifics about this person jumping. I haven't told you what initial and final are. And that's because there is not necessarily, you get to decide. Okay, now let's talk about what should I probably decide to make my life easier. Okay, where is one location that I should probably look at mechanical energy, and why should I look there? I would say that makes sense. Why does that make sense?
That's the changing part of the forces.
It's simpler than that. What are we trying to find? We're trying to find K, which is the spring constant, which is in the equation for elastic energy. So why are we looking at that spot?
That's where
That's the only spot where it really has elastic energy. Right? Now, I could look above here when it's a little bit stretched. The problem with that one, the other nice thing about the bottom is what is going to be 0?
Gravity?
No.
Or no?
Kinetic energy. Why will kinetic energy be 0 at the bottom? Not moving at the very bottom of the stretch, right? So I could look 0.2 meters above that, but then I'm going to have elastic and I'm going to have kinetic. In order to get kinetic, I need to know the speed. I don't know what the speed actually is. It doesn't tell me anything. We haven't calculated anything about speed. So that's going to make it more complicated. All right. What other spot should I look at? Makes perfect sense. Why does it make sense to use the maximum height? Besides the fact that I straight up gave you those 2 particular distances.
I mean, it's also not kinetic energy.
There's no kinetic energy, there's no elastic energy. It's going to make things a little bit simpler. Yes. All right. Next, so what we do here, from here, is actually I'm going to change this. Instead of saying initial and final, and you're welcome to use initial and final, but that's kind of confusing because it's going back and forth. I'm just going to say top and bottom, or stretched and, I mean, what the heck you want. Let's go bottom and top. Okay, what are, so mechanical energy. What are the types of mechanical energy changing in this situation? Kinetic. Okay, so I'm going to say kinetic at bottom and kinetic at top. Okay, yeah, it's all of them. Gravity at the bottom plus gravity at the top plus elastic at the bottom plus elastic at the top. Now, I talked about this yesterday. Gravitational energy can be a little bit weird. Okay? The reason gravitational potential energy can be weird is the sentence that, okay, this ball is on the ground, does it have gravitational energy? The answer is, the correct answer for you is to say compared to what? Because compared to the ground, the answer is no. And that's what people usually make an assumption on. But, as I mentioned on Friday, I alluding to, it's a hole in this piece, right? Somebody cuts a hole in this, does it have gravitational energy now compared to the second floor? Yes, and compared to the bottom floor. So the point of that is you get to decide the 0. Okay? So like I would go down here at this spot and go, does it have gravitational energy? And the answer is it depends on where you put the 0. You understand what I'm saying? Okay? Point being, you get to decide where the 0 is at, so you need to place that in your problem. Now I would argue that there are two logical places to put the 0 in this circumstance, you need to understand where. So where would be the two places where you would like logically put 0?
At the bottom.
Either at the very bottom, or
0.4.
I would say, yeah, right there where the thing is stretched. Okay? I'm fine with either. Okay? Which one would you like?
The bottom.
Bottom makes the most sense. Okay? The bottom makes the most sense because if the 0 was here, what would that mean about gravitational energy?
0.
Be negative. Because if that 0 is here, then this would be negative because that height would be negative 0.4. Now that's fine, but a lot of people will do this without thinking about what change that actually means. And what change that actually means is, what is the height at the top then?
2.
No,
2.4.
2.4. Because it's not measured, it's measured from the 0, right? If you had placed the 0 here, then the final height would be 2, right? And the initial height would be negative 0.4. But since you put the 0 there, which is completely fine, you just have to recognize that that means initial height is 2.4. Make sense? All right. So let's go to this. Okay. The three things we knocked out ahead of time, okay, to start you off with this problem, to help you with when you do your problem, is I identified what two spots we were looking at, okay, kind of logically placed out why. The second thing did was we filled this out, and we filled it well with all of them, but you have to fill it out with things that are changing. We did the last two examples last Friday in which not everything was changing. And the last thing I mentioned is placing zeros specifically for gravity. Now you don't place, here's the other weird thing here. You don't place 0 for elastic. Okay, 0 for elastic has to be in equilibrium. So the other weird thing about here is that technically there is still a 0 here, right? It's not the 0 for gravity, it would be the 0 for elastic in that case. All right, that being said, let's cancel what cancels. What cancels out?
Initial, or B, kinetic.
B, kinetic, agreed. Because it's not moving at the bottom.
B, gravitational.
Bottom gravitational because of where you just put your 0.
Wouldn't your other kinetic?
Agreed. Now, this brings me to the point that some students go, well, Spainhour, you told me if it doesn't change, I don't have to write it. Why did I write it here? What I mean by that is throughout the entire problem, it doesn't change. If kinetic is changing in the middle, which you'll see why this is the case in just a second, I still want you to write it up there and cancel it appropriately. I believe there's one more. Elastic at the top. Right. Because is there potential energy of elastic? Is there an elastic pushing on the person at the top? Nope. So there it is. So as complicated as this starts, the math actually arguably gets kind of easy. What is the equation for elastic potential energy?
1/2
And I'm going to call that delta XB. Okay? Specifically, this subscript is associated with this side because that's the delta X, of course, at the bottom. Equal to, what's the potential energy of gravity equation?
mass times gravity.
Oh, with the same thing I just said, you should put a T somewhere in there. Height T, yes. The reason, by the way, I'm not putting subscripts on everything else is because they are just staying the same throughout. Mass is not changing, gravity is not changing, K is not changing. So from here, we're trying to find K. It's some complicated algebra. Well, not complicated. You got this. What should I do first?
By 2.
Multiply by 2. Then what?
Square.
Nope.
Or divide by x squared.
Divide by delta X squared. I think that's it. So let's plug numbers in. You said 2 times 70 kilograms times G times the height at the top was what?
2.4.
2.4 meters. Divided by 0.4 meters squared. 140, 1400, 2800. Ooh, that's going to be a big number. Divided by 0.16. So about times 5-ish. 2800. I'm going to go 13,000.
I got 20,500.
Very off. Why am I so
I do rough for
No, I got the same thing as you do.
I was right there. was right there.
There would be just
I was wrong. It's 0.4 squared.
It's okay. We're still kind of
You don't have to be. All right.
yeah.
So what do you want to write down as the answer? What's the answer?
20,850.
Okay, I would write down 20,600. And what are the units on that? Based on what we have discussed about springs, is that probably reasonable?
no.
Yeah.
No, definitely not reasonable. Okay, that is a ridiculously high spring constant. And admittedly, we are dealing with spring constants, not like all of the numbers, but we kind of talked about this ahead of time, right? 0.4 meters. 0.4 meters is about 40 centimeters. You're talking about like this, okay? And then 2 meters would basically be you just jump from here. Let's see if I can do this. You stretched it this much, and you made it all the way to the ceiling. I mean, I don't know. Maybe I'm not. Maybe that is relatively reasonable. But it seems somewhat large for me in this case. All right. Now, here's a question that is very reasonable to do now that you have solved this, okay? And checks to make sure you understand everything else. How fast would the person be going? How fast would the person be going at the equilibrium when it's no longer stretched? Go ahead and calculate that. How fast is the person going right here? Right when they take off from the trampoline. How should you begin this? By the way, this number can now be part of your given if you prefer. It's that one right there.
No, that one.
Yep. I'll put spaces here because you got to fill those in.
So what does the capital mean?
Mechanical energy. So, what you guys missed on Friday, I think everybody else should be able to go here, see this stuff, or be able to answer without looking at that page directly. Back to the tree thing is this, okay? Conservation of energy is a thing. The conservation of energy, if I was going to do that, would look like this. Energy initial equals energy final. And what it would have on both sides is all the types of energy that would be particularly changing. So in my example where the ball drops on the ground and all the energy actually goes away, we would probably put gravitational on both sides. We would put kinetic on both sides. We would put elastic on both sides. Okay, but then we would also probably put sound and thermal and anything else that possibly changes. And as those are ridiculously hard to measure, one of the things we discussed at length was how conservative forces will basically make mechanical energy go to other mechanical energy. Pretty much if everything is conservative, all the energy is going to stay over here. Now we talked about the fact that's not reasonable, but it is in some cases pretty close to straight up accurate, even if it's not quite perfect. Okay, if there are any non-conservative forces, conservative forces, well, now the energies go back and forth between the sides and it becomes a lot more complicated. The biggest culprit is friction, but a non-conservative force is basically everything that's not conservative, and the only two conservatives are gravity and elastic. All right, let's see what you got on this problem. So what two spots do you want to compare?
The top and the zero at the equilibrium.
Okay, that's completely fine. Now, if you do that, if you compare the top to right here, that'll work. As we've already stated, since mechanical energy is conserved, you could also compare the bottom to right there. Both are completely fine. So you said top, so let's go top. What did you call this like center spot?
I call that initial.
Initial, sure. See, the initial's kind of hard because I'm imagining a person just on the trampoline. By the way, if conservation of mechanical energy is a thing, does this human actually have to push?
No.
No. What you do when you push down is you do non-conservative work to add energy into the situation to fight all the energy that's being lost by what's probably the primary thing taking energy out? Friction. And actually, it's probably not air friction. It's probably friction in the springs, which is proven by the fact that you hear a very loud sound when you hit those springs, and that's where all that energy is specifically going. But I don't necessarily love initial for that spot because, again, I'm just imagining a person going up and down, up and down, up and down, up and down forever. So I don't know. Let's call it equilibrium, or just E. So starting at the same spot, we do the same things. Okay, comparing the top and the bottom is gravitational changing.
Yeah.
Yes. So I'm writing. Oops, I did the thing. Cool. Is kinetic changing?
Yeah.
Yep. Is elastic changing?
Yeah.
Arguably, no. Not from the top to equilibrium, it's not. Like if you just imagine a person like that just dropped into that situation, starting at the top, going all the way down. There's no elastic force on them throughout. Now, if you put it, no big deal. You're going to see the. I want to point this out because I'm going to say you don't have to put it, but if you did put it, it's not going to hurt because what are both of the elastic energies going to be? Zero, because there's nothing pushing on them up there, and if it's at equilibrium, there's no spring because delta x is 0 for that guy right there. Okay, what else cancels here?
I did equilibrium with bottom.
Okay, well, I will do both then. I'll do both by doing it like this. Well, in your case, actually, I will do it separately. Mechanical energy of bottom equals mechanical energy at equilibrium. So that would be potential is going to change, right? Elastic is going to change. And kinetic is going to change for you. All right, let's go over here first. Cancel what cancels. What do you got?
I said kinetic initial or kinetic bottom.
Kinetic at the bottom is going to be 0. Okay, that's true over there. What about on this one?
Kinetic top.
Kinetic top will be 0. Okay, I'm going to focus on this one first, but then I'll hit the second one because you can do either way. Okay, here's the tricky one. Does gravitational change?
Yes.
I'm sorry, I said that totally. That's totally on me. Does gravitational cancel on either of these?
I was saying the bottom. That's what I did.
Okay, so here's my thought as to that. If you set up this problem ahead of time, one thing that's kind of confusing here is that you could make that argument. You can move that 0, and that is completely fine, but it can be a little bit confusing. Okay, so I personally, and this is again a personal preference, I'm not going to take off for this if you don't do this, I personally like to leave the 0 where it is throughout the entire problem. Okay, if that is the case, then should there be gravitational right here?
Yes.
Yes. Okay, so that's why it's kind of confusing. But in your case, you're saying no, so what are you? You're technically just moving the 0 back here, which is fine. You just move the heights around accordingly, and that's complete. That's why I say it's kind of a personal preference, because it's not the worst thing in the world to make that change, but you can see where it can somewhat be a little bit confusing. So in your case, you're going to say, I'm going to move the 0 to here for gravity, in which case, yes, that would mean that at equilibrium would cancel. In which case, you would be left with mass times gravity times height at top is equal to 1/2 mass velocity at equilibrium squared. And do you need to know the mass?
No.
Nope. And actually, I would say yours is probably the easiest here. Multiply 2 on both sides, square root both sides, and you should get the right answer. Okay, so go ahead and do that. I'm going to come over here and talk about this one. We should end up with the exact same answer because it is the exact same situation. But for somebody, instead of going top to equilibrium, goes bottom to equilibrium, what else cancels over here? Where did you put your 0 for gravity?
The initial.
It's the same spot we did on the first problem? Okay, which would mean that this is in fact 0. Okay? What else is going to cancel?
It's elastic.
Where?
Equilibrium.
Elastic at equilibrium is going to cancel. Oops, I did the wrong one. I totally did the wrong 0. My apologies. On gravity. My bad. This one should be a 0, and that one should be a 0. Okay? And finally, what's that? Or does it? Maybe I'm wrong. Oh, it doesn't. No, you're right. You're right. That's it. So yours would end up as potential energy at B would be 1/2 K delta X B squared is equal to mass times gravity times height of equilibrium. Okay? Plus 1/2 mass velocity to equilibrium squared. Does your mass cancel? No, because there's not a mass in every single term. So you can see your algebra is going to be a little more complicated. It does end up hopefully the exact same way. Let's check to make sure. First thing that I would do is I would subtract that on both sides. Then I would multiply the whole thing by 2. I would do this on another line, but I'm just going to try to go quick here. I divide the whole thing by m and square root the whole thing. And that's what you should end up with. And if you've done this correctly, you should end up with the same thing. Now, I will tell you, you're going to get slightly different answers because I'm going to go ahead and guess that you're going to use the k that was rounded and not the exact k. Whereas you'll notice actually here that that Henley doesn't have to use any of the numbers that it could just use the originals in this case. So 2g times 2 meters, square root. You can definitely see that Henley's is easier to calculate. 410, so that should be 6 and change, right? 6 point something? 6.26. And then if we come over here, this should be 2 divided by 70 kilograms times 1/2 times 20,600 newtons per meter times 0.4 meters squared minus 70 kilograms times g times height would be 0.4 meters. Let's go ahead and put brackets on that. And if we've done this correctly, pretty darn close to ending up the exact same way.
I got 7.4.
Well, let's check. Again, it could be a rounding thing, but let me check. Let's go 0.5 times 20,600 times 0.4 squared. Okay, minus 70 times 9.8. Oops, times 0.8 times 0.4 times 2 divided by 70 square root. I got the exact same thing. 6.26. All right, let's do this one more time. You have a situation, both of my sisters actually, when they were in college, did a whole thing where they went over to Uganda and did a whole like bungee jumping thing over the Nile. So I made a problem. If you don't like my whole example, it's just this person over the Nile. But we've got a person up here, my sister, so 55 kilograms. There we are. Okay, boom. The length of this bungee cord, okay, the length of the unrested bungee cord, so I'll call this length 0, is 20 meters. The height to the water, the Nile below, is 60 meters. They're actually going to stop about 5 meters above the ground, or 5 meters above the water. Yes. There's no sharks in that. Just being dumb. Because they do that sometimes. Okay, so they're going to start up here and they're going to end right here, about 5 meters above the water. And the question is, what is the K value of that bungee cord? See if you can't. I think I gave you all enough information to make sure. See what you can't do about solving that problem. Let's talk real quick about why we know this is conservation of mechanical energy. Number one, I haven't said anything about air friction, so if I don't say anything about air friction, it's pretty fair to assume that we're going to ignore it. Okay, there's no surface friction here. So what are the forces doing work here?
Gravity, elastic.
Gravity and elastic, and so we can use conservation of mechanical energy. So we go over here. I would say that this would absolutely be a reasonable spot to use initial and final. You're always welcome to use initial and final, just know some of their limitations when you've got a situation where a person's, especially like the roller coaster one, when there's like 3 or 4 different spots you're looking at, it becomes a lot more challenging to talk about initial and final because there is no specific initial and final. All right, so let's start where we start. Let's go potential energies first. Is gravitational potential energy changing?
Yeah.
Yes. So I'm gonna write it on both sides. Is elastic changing?
Yes.
Yes. Is kinetic energy changing?
Yeah.
So we got all of them again. Now, when you, for some of you guys that are struggling maybe on what cancels, the first thing that you're always welcome to do, if you don't know why there are cancels, write out its equation in its entirety. Because the equation for kinetic energy, the equation for elastic energy should cancel when what's the case? When should this be 0?
Displacement 0.
Yep, AKA the thing is not stretched, right? When should kinetic energy be 0? Oop, screwed that up. It's not moving, or speed is 0. And when should gravitational be 0?
When it has when it's on the ground.
0 height. But careful with the on the ground thing, because as we've talked before, it's really up to you where you set the zeros at. But it's when height is 0. All right, so where do you want to make height 0? I would argue there's 2 decent spots.
At the bottom.
I could see you saying 2 different. What do you mean by at the bottom?
At the end of its stretch.
Okay. I could totally see you putting that there. I personally like the water being 0 in this case, so if you like that, don't feel bad. But of course, then something's not going to cancel a little bit later. We can certainly do that as well. We'll make that the 0. Okay. That being said, what cancels?
It's elastic potential at the start.
Elastic is 0 at the start because
It's not stretched.
not stretched, and kinetic is 0 at the start because
It's not moving.
cool. So when you're doing this, you don't need to try to look at it the entire time. You can literally, to make those zeros, look at her when she's in the initial position. And again, delta x is 0, so that's why that cancels, and not moving, so that's why that cancels. But we do have gravitational because it do have a decent height set from 0. Okay, next on the final side. So she's right here now. Okay, what cancels?
The gravitational potential.
Gravitational cancels because of where we put our 0. If we had not put our 0 there, then there would still be some. And
Yeah.
what's that?
Kinetic.
Kinetic. Once again, you'll see that kinetic technically does not change because it goes from 0 to 0, but we know that kinetic's changing throughout this particular problem, so that's why it's a good idea to put it on both sides. All right, from here, this is remarkably similar to the trampoline problem. This is just going to be, how do I calculate this?
Mass times gravity, or I.
Correct? Is equal to 1/2
Okay, delta x.
squared. And what's my algebra? Multiplied by 2 divided by delta. This is exactly the same as the last one. So Sveinauer, why did you do this problem if it's the same as the last one? The main thing is the next part that I wanted to address. Given what you said, what is height initial? 55. That's good. Okay. Next, and slightly more challenging, what's delta x?
Could it also be 55?
No.
Negative 55.
No.
60.
No. What is delta x actually?
Oh, 0.
No. No, then it would be 0. It's definitely stretched. I'm asking, what is delta x in terms of the measurement? What comes from the spring force? What is the delta x in that spring force?
How far it's stretched.
How far it's been stretched. So why is it not 55? Not 20.
It's 20 plus the distance you walk.
Stop guessing and think about it. Give yourself a half a moment. Let me ask you this. Yes.
It's stretching 60.
Nope.
So what's
Let me ask you this. As the person starts falling in the first 10 meters, is it stretched?
Not entirely.
No. Delta x would still be 0. Okay, negative is unnecessary here. When will it start to be stretched? It's 35.
I knew that.
I bet you did. You probably should have said it to begin with rather than a whole bunch of wrong answers there. Why is it 35?
Actually, answer.
How far does the person go in total?
55.
55. However, is it stretched the entire time? No, it's not going to be stretched for the first 20 meters. The stretch is going to occur once we've gone 20 meters. So from here to here, that is 55 minus 20, or 35. So plugging this in really quickly here, we have 2 times 55 kilograms times g times height initial is 55 meters, all over 35 meters squared. What do you get?
1,694.
That seems too big.
Is that 56 kilometers?
55.
Yeah, 4.49.
That seems too small. What did you say?
4.49.
No, it's 48.4.
That's just right.
What would the units on that be? So it should be, here we go, 2 times 55 times 9.8 times 55,
Oh,
right? Divided by 35 squared.
Oh, I didn't put squared.
Gravity will do it. Yeah, I figured you did. All right, this is 44. Now, let's do this. I've been giving bonus problems the next day, and I've been unhappy with how I've been getting problems for the next day and being unhappy with how they have ended up because I have required it and I don't want to grade it because a bunch of you aren't doing it. So let's do this. Bonus problem. Okay, this exact same setup, that number also included. The question is, how fast is she going after falling a total of 30 meters? Okay, so do that for tomorrow. It's bonus. If you don't do it for tomorrow, no problems. You just show me when you get here tomorrow, and you'll get bonus for doing this problem decently more than the other homework. So again, after falling 30 meters, how fast is she going?
Got the whole game together.